So we've learned about Charles' law and Boyle's law, two of the ideal gas laws. Today we're going to learn about a third gas law, and we're going to learn how to figure out which of those gas laws fits a particular problem. So if you don't remember about Charles' law and Boyle's law, make sure you go back and look that up or review. So the homework problem that was assigned says if 12.6 liters of carbon dioxide is held at a temperature of 25.0 degrees C and is cooled until the volume shrinks to 9.5 liters, what temperature will be reached? And so far, we've only dealt with two gas laws. The first gas law was Boyle's law, P1Z1 equals P2Z2. And the other gas law we've dealt with so far was V1 over T1. This is Charles' law. And there are some others, but right now those are the only ones you know about. So what we want to do is take this problem and make a list of knowns and unknowns, or knowns and unknowns singular, I guess, and see which one of these two equations actually fit that list. So we have 12.6 liters, that's a volume. So we can say volume 1, 12.6 liters. It's held at a temperature 25 degrees C. Now the problem with that is that you can't use temperature in degrees C. You've got to convert it to Kelvin. So we're going to say 25.0 degrees C and add 273.15 to that. This is the conversion to Kelvin. Notice we have an empty slot over the 5, so they're going to do some rounding off when we're done because we're adding together. 298.15, you've got to round off its 5 here. And this is Kelvin, so 298.2 K. 298.2 K. Always show all the work because I'm from Missouri. Okay. And then we got, it says this is going to be cooled now until the volume shrinks. So this is a new volume. You have to be able to read the problem and interpret what it's asking for or telling you about. We got 9.5 liters, and it asks what temperature we're going to have. Now the question doesn't say that you have to convert it back to degrees C. So if it doesn't ask you for it, you could just leave it in Kelvin. So we have V1, T1, V2, T2. Well, that's Charles' law here. Okay. If you just know what the various gas laws are, you just pick the right one. So we're going to first list all of our knowns and unknowns. And I can see now that I'm going to have T2 on the bottom, and you cannot solve directly for a temperature that's on the bottom of a fraction. So at some point we're going to have to flip. You could flip now and then plug everything in, or you can plug it in and then flip. Okay, either one works is fine with me. So we got 12.6 liters over a temperature of 298.2 K. And then 9.5 liters over T2. And then the way that I'm doing it here, I'm going to flip at this point because I can't solve directly for this temperature on the bottom. So I'm going to write that as 298.2 K over 12.6 liters. And that's going to get the T2 on the top because I'm flipping both sides. And 9.5 liters. And now we want to set it up to cancel everything except the unknown, if we can, on one side of the equation, or equal sign or another. And the way we're going to do that is to put 9.5 liters on top here so that this actually cancels out 9.5 liters, leaving us with T2 by itself. But you can't forget that whatever you do to one side of the equality, you must do to the other, or that doesn't remain equal. So we've got to put 9.5 liters over here over 1. This allows us to cancel all of that, leaving us with T2 by itself. You don't have to circle T2, I just did that to show you we have it by itself. We can cancel units of liters. Kelvin is what we have left, and that is a temperature unit. So because it's now left equaling T2, we know we've got the right units. We probably set it up right, at least at this point in time, with these simple equations. The only tricky part here is I've got to round this off to two significant digits. And anytime you're getting rid of a digit in the ones place, you're supposed to write the answer in scientific notation. So we're going to move our decimal place 1, 2 places. And then we're going to write this as 2.2 times 10 squared Kelvin equals T2. Okay? Alright, let's look at a new equation, which really isn't all that new. It's just combining Charles' law and Boyle's law together to make what's called the combined gas law. Alright, so we've looked at Boyle's law. And we said this is the practical expression of Boyle's law. We looked at Charles' law. And if we're looking at the same gas, this volume is the same. Okay? You got volume 1, volume 2. Well, there's volume 1 and volume 2. If it's the same gas, you can actually put this together. I don't know how to actually express that. I'm going to put brackets around it to show us putting these two equations together. And we get P1 V1 over T1. We're learning about a new gas law. Okay? Alright. So we're combining Boyle's and Charles' law. In fact, we're also combining a gas law that, at least in this class, we don't really spend any time with, and it's called Gay-Lussac's law. But when you put them together like that, since we're combining the gas laws, we're going to give it this really special fancy name here, the combined gas law. I'm doing this instruction in an honors class, and these are the references that you get to use on tests in an honors class. And if you look really, really carefully, you actually have this equation on your references. Okay? Now, Boyle's law and Charles' law are not there on your test references. But if the temperature doesn't change, you don't have to worry about it. And so what you have is just P1 V1 equals P2 V2, and there's Boyle's law. Okay? If the pressure doesn't change, you can drop the pressure, and you got V1 over T1, V2 over T2, and that's Charles' law. Okay? So while all three equations aren't there, they're kind of all there, aren't they? Okay? Does that make sense? If it doesn't change, you just don't include it in the equation. If 25.00 liters of hydrogen at negative 10.0 degrees C and held in a container with a flexible volume under 2.00 atmospheres pressure is warmed to 30 degrees C and the pressure is eased to 1.50 atmospheres pressure, what would the volume be? The conversion to Kelvin is, if you have a temperature that's in degrees C, okay, a temperature in degrees C, you add 273.15 to that, no units on this, and that's going to give you the temperature in Kelvin. Does that make sense? So if you have it in Kelvin, you need to go back to degrees C, you have to subtract. If you're just going from degrees C to Kelvin, you add. Okay, so we got our guest teacher here. It never hurts to take a minute and write it down on paper, okay? So when you're converting negative 10 degrees C to Kelvin, put negative 10.0 degrees C, put in 273.15, and you get 263.15, and by lining it up vertically like this, you can clearly see that you've got to get rid of that digit when you round off. Does that make sense? And so what we're going to get here is 263.2K. We can. All right. So we need to have the significant digits right. The same is true when you're converting the 30 degrees. A better solution would have been to put in this 2 atmospheres he had here. And I like to use a time sign, but putting in parentheses is perfectly okay. Over 263.15K. And then we're going to say that's equal to, slide up a little bit, okay, 1.50 atmospheres times V2 over 303, it should be 0.2K. As I talked about rounding off, let's go ahead and do that. And then you can just take both of these and put them at one time. 1.5 atmospheres can go on the bottom. 1.50 atmospheres and 303.2K can go on the top. And what you do to this side, you got to do to this side. 1.5, whoop, I'm sorry, 3.30. Yeah, you cancel all at one time, kind of speeds it up a bit. And that allows you, like you said, to cancel everything kind of all at one time. 1.50 cancels here, 303.2 cancels there, Kelvin cancels here, atmospheres cancels there, and you just put it in the calculator. Remember, the way you do it when you have two things to divide by on the bottom, the quick way that always works with every calculator is this times this times this, hit equals, divide by this, hit equals, divide by that. That makes sense? You're still going to come up with the same answer you came out with, although your unrounded answer might be slightly different. 3.67 milliliters of oxygen is held under a pressure of 950.0 torr. Now, torr is one of the pressure units. If the oxygen obtains a temperature of 5.00 degrees C after squeezing, which means compressing it, to 2.37 milliliters under 900.0 torr, what was the original temperature? All right, so I'm going to read the problem and I'm going to figure out what do I have, what am I trying to find. Okay, now it says I'm starting with 3.67 milliliters of oxygen. I'm going to write that down. That's a volume. And it says I have a pressure I'm starting with of this 3.67 milliliters of 950.0 torr. Pressure is P sub 1, 950.0 torr. The oxygen obtains a temperature, so we're changing the temperature. Okay, so I've got a temperature 2 over here. Temperature 1 hasn't been stated yet. 5.00 degrees C. I can see I need to change that into Kelvin. I'm compressing it to 2.32 milliliters. So at this second temperature, it has a new volume. So that's volume 2, 2.32 milliliters. And it's under a pressure of 900 torr, P2, 900.0 torr. All right, now, and then it says, what was the original temperature? So it's saying what was the temperature up here in the beginning when we were first starting. So temperature 1 is what we're trying to find here. Okay? So we just simply figure out, okay, which equation do I need? Well, if I've got volume, pressure, and temperature, that must be the combined gas law. You need to know that you've got to convert the temperature here into Kelvin. So we've got 5.00 degrees C. I'm going to add 273.15 to that. 278.15 degrees C. And there's nothing to round off here because there's no empty slots. So this is going to equal 278.15. I'm sorry, that's not degrees C, that's K. Okay, so that's K here. All right. And then we can write out the equation we're going to use. P1 V1 over T1 equals P2 V2 over T2. Plug in what we know. We know pressure 1, 3.67 milliliters. We know volume 1. I'm sorry, that's volume 1. Pressure is 950.0 torr. I just flip these around. This is volume here, this is pressure here. And T1 we don't know. And over here on this side we're going to have, since I flipped around the volume and pressure, I'm going to flip them around here. 2.32 milliliters, 900.0 torr, and that's over 278.15. Alright, I can't solve for a unit like this T1, I can't solve for it while it's sitting on the bottom. I've got to flip both sides. Now, it's fine with me if you flip this equation first. Doesn't matter which way you do it. I'm just showing you how we get to this point where T1 is on the bottom and we need to put it on the top to make sure we can solve for it. Yeah, you can flip it initially if you want to. Okay, so I'm going to put T1 on the top. I'm going to put 3.67 milliliters times 950.0 atmospheres. I'm going to flip both sides. If you do it to one side, you got to do it to the other. I don't know why I put a time sign. That's an equal sign. Oh, thank you. 278.1, and that's, I didn't put the K down here either, did I? 15 K. And then we're going to put the 2.32 milliliters on the bottom times 900.0 torr on the bottom. Okay. And this is why it's nice to have the paper turned sideways, because I don't really have enough room to solve here on the outside. Okay? So I'm going to change this over to the paper and we'll turn it sideways. Alright? So I've got a little more room to work with. Put the equal sign in the middle. T1 on the top. 3.67 milliliters times 950.0 torr. Over here we're going to put 278.15 K over 2.32 milliliters times 900.0 torr. Now maybe you write really, really small. You don't need to put it on the paper like this, but I don't write so small like that. And what we want to do is to get T1 by itself. And the way you're going to get T1 by itself is to multiply by these two things on top of our fraction over here. 3.67 milliliters times 950.0 torr over 1. And what I do to this side, I've got to do to the other side. 3.67 milliliters times 950.0 torr over 1. Okay, so I did it to both sides. I can go through and cancel. I can see that I can cancel all of this and all of that. And I've left myself with T1 by itself, which is part of the goal of solving these problems. I can cancel out milliliters here and here, and torr here and here, and now I can put it in the calculator. This number times this number times this number, hit equals, or enter, divide by this number, hit equals or enter, and divide by this number, hit equals or enter. So 278.15 times 3.67 times 950.0, hit enter, then divide by 2.32, enter, and then divide by 900.0 and hit enter. Okay, and we get T1 equals 464.449 and a bunch of other numbers, which aren't really going to matter in the long run because I'm going to round them off. That's the 43. And the units we have left is K. We want to round this off to 3 significant digits because this is the measure to calculate a number of the problem with the least number of digits. 3.67. So there's only 3 digits there. So we're going to underline everything after the first 3 digits, 1, 2, 3, underline, round off, and you get 464K. And the problem didn't ask you to change it into degree C, so you could stop there. So you got to talk a calculator's language, okay? And so that's why I teach you that kind of a shortcut system where you multiply everything on the top, hit enter, divide by one thing on the bottom, hit enter, and then divide by the second thing on the bottom, hit enter. There are some calculators that will handle it when you put it in the way you describe. Some won't. So this way works with every calculator that I know of. And you can always go through the process of multiplying all of this, writing it down, multiplying all this, put it underneath, and then divide those two numbers. But that's an extra step in putting numbers in your calculator, and it kind of slows you down. What I've done here is to give you some homework that has 3 different problems. And so at this point, you've got to figure out which one of the 3 gas law equations we're working with is going to work for these problems, okay? Got to choose the right gas law equation, okay? Charles' law, Boyle's law, or the combined gas law.